Hey guys, and welcome to our webinar today, Mastering Tolerances for Machined Parts. Thanks so much for joining us. I'm here with Greg and Jason, but first I want to introduce myself. I'm Serena, and I'm here on the marketing team at Zometry. Couple of quick notes before we get started. Please submit your questions in the question box throughout the webinar, and Greg and Jason will answer them at the end. We'll also send around a webinar recording at the end, so you can share this webinar with colleagues or rewatch it yourself. And stick around until the end of the webinar for a special discount code as well as t-shirt offer. So thank you for being here. Next, I want to introduce our presenters, Greg and Jason. There he is.
Hey, hey.
So this is Greg, our Director of Application Engineering at Zometry. Greg brings many years of experience and leadership to our team here at Zometry. He's an expert panelist and speaker in all things CNC machining and additive manufacturing. He's also the star of our Engineering Challenge videos. You may have seen them. They're called the Will It series. Before Zometry, he was a project engineer for many years doing rapid prototyping, so he brings subject matter expertise as well as manufacturability expertise. So, and then we also have Jason McClure, VP of Manufacturing and Quality. Jason is an expert CNC machinist with over 25 years of experience. Jason is a Xometry OG and led our internal CNC machine shop for 4 years. So now he oversees the quality and manufacturing partner tech support departments. And before Xometry, he was the chief manufacturing officer at M&D Machine in Baltimore, Maryland, which specializes in complex aerospace and defense parts. So with that, I will pass it over to Jason and Greg.
Serena, thank you so much. And guys, we're really excited to talk today about CNC tolerances. There's a lot of question marks around this, especially when it comes to what you're putting on drawings and how that is perceived by quality assurance and what it takes to actually machine those parts to those tolerances. We're here to help answer those questions. As you go through this webinar, make sure to use the questions box that you can see on the GoToWebinar panel there. Put in any questions that you may have as we go along, and we're going to answer as many as we can in our question session at the end of our presentation. I also want to give another shout out to Serena. She is behind the scenes of all these great case studies that you see coming out at Zometry and all of our content related to a customer success story. And if you do have a customer success story that you want to share as well, please reach out to Serena. She'll make it awesome, and we love to do cross-promotion and cross-branding as well. So today, it's about tolerances, and my agenda is right smack dab in the middle, a bunch of general machining tolerances, specific tolerance guidelines. For those of you who are new to Zometry, I'm going to start off with talking about what Zometry is, what our business model is, as well as for those of you who use Zometry, you may not have been on the site for a bit, and even in the last couple of weeks, you've done some major improvements to the site that I'll be able to highlight. So I'm going to do a quick demo here to get started. So again, as we're going through, use that question panel. I can't say it enough. We work best with that, with questions and answers. So Zometry, who are we? What do we do? We are this manufacturing platform. We actually inject technology right into the traditional RFQ process by allowing you to upload a 3D model that you've designed. We instantly interpret it, price it out, and give lead times in multiple processes from machining, sheet metal, injection molding, and 6 to 7 different 3D printing processes as well. So you're able to get these quotes, specify your quotes even further, and I'll show you how to do that very quickly here. And then just click and check out, like I said, Amazon.com. Like, it's a very clean e-commerce experience for what typically is a opaque traditional process. So we've really brought transparency to pricing, to lead times, and allow you to choose very quickly on our website. Our fulfillment is backed by a partner network of over 3,000 machine shops. A lot of these are small business manufacturers all across the US. We also have some international partners as well. And what we're able to do is actually take a look at the specific needs of your project, so on a part-by-part basis, and find who's best at making those types of parts to those specifications, and pair that up. So we're your matchmaker, we're your supply chain manager, and we utilize our vetted partners to fulfill this work, and we hold everything to Xometry's quality standards. So let's jump into the platform real quick, and I'm going to make this very quick because we have a lot of content to cover today. So let me go through. So I'm starting on our homepage because a lot of this starts up front. Even if you don't have a design yet or your project's just starting, please use Zometry as a resource. We have plenty of FAQs. As Serena mentioned, we have videos. We have our design guides. We have a design guide for every process that we offer. So if you want to dig deep into CNC machining, for example, or say you're the best in the world at CNC machining, but you know nothing about metal 3D printing, go to our design guides, check that out. Check out our FAQ. It's exactly what it stands for. Some quick questions about general tolerances, etc. You could go there, check it out. And there's some other great stuff here, like photo galleries. So a lot of people are looking for example, 3D printed surface finishes. I want to highlight that stuff as well. So let's go get a quote. Our quote site makes it very easy to get pricing. I'm going to go ahead and use a part from recent uploads, but the speed is the same even if you're uploading a part directly to the website. As soon as you upload, so I'm going to take this display frame here, you get a price. That's how quick it is to get pricing and lead time. This number right here, it's actually priced out in the least expensive process that we have for this geometry. In this case, it's actually a 20 by 20 inch panel here, and we can print this in 3D printing FDM for the least expensive amount at quantity 1. I'm going to show you how to specify this even further, turn it into a CNC part very quickly. So I'm going to go click Modify Part. You'll see a 3D preview of the part in question here, and you can tell I've designed this for CNC machining. Those nice round internal corners here. I could do some sharps on the externals, and everything is more like a pocketed piece of aluminum. That's what I've designed this for. So let's say I'm going to make 4 panels here. I'm going to CNC machine these. I'm going to make them out of 6061, but we have a bunch of materials available. So let me go find 6061 here. And you can see my pricing's already instantly updated. So I can see my standard price, I can see an expedite price, and our new economy option as well, which shows the pricing if we do this with an international partner. You can further specify the finishes. So let's make this a nice Zometry blue anodized here. I'm taking a look at my part. I have some of these blind holes back here for taps. So I'm going to put in 4 threads and tapped holes. You're going to see our website's going to ask for a drawing because we want to know where these tapped hole features are and what size a tap and how deep the taps are needed. This is where a lot of this presentation begins. It's asking for these specifications from a drawing for tighter tolerances. And on tolerances, I'm going to go further into this. So I'm just going to highlight that you can select your tightest tolerance, select how many tight tolerances you have, and that's all we need to price. The drawing will do the rest for us once it gets into the machinist's hands, but that's what we need to price. You can further specify things like surface roughness, part mark requirements, inspection. All these things dynamically update your pricing and lead time on the fly. Once your design is ready, you can add more parts to this order just by adding or clicking and dragging more pieces in. You could add things like certification. So if this is an ITAR job, you're 1 click away from that. CSCs, material certs, hardware traceability, all that is a checkbox away. You could choose what level of expedite you need and continue the checkout. If you are not the purchaser, so if you're an engineer and you're using this more as a quote management tool to get pricing, feel free to use some of our share options. Most popular is the PDF option, where you click that PDF, you can download and save. That quote is valid for 30 days, and you can share that with your purchaser, and they could just send us a PO with that PDF for reference to support at Xometry.com. So there's lots of options here at Xometry, lots of configuration, whether it's prototype or production, but one site and a few clicks away from making all that happen. Whew. All right, let's go to tolerances. So again, CNC machining, sheet metal, plastic 3D printing, metal 3D printing, urethane cast, and injection molding, all this is under the Xometry umbrella and a click away. Tolerances. All right, so it turns out, and I figured this out over a decade of working with design parts, that most of the time people design parts to be used in reality. And this is why tolerances exist. There is variation, and there will always be variation in parts, even if it's very minor in a manufacturing process. What tolerances are is a way to describe what level of variation is acceptable for the purpose of that part. For each process, we have general tolerances or manufacturing general standards for those processes. We actually will follow through those, and there's a kind of standard. They're almost like a blanket over that part. But what we are interested in is those specific tighter tolerances. So something that is tighter than the general range. And that's what we want to highlight via the website to select, as well as for machinists in production or QA. That's what we're really looking for to pass that part. So to know what's tighter, we need to know what's general. This is our CNC machine tolerances here. This is something that you can find on our manufacturing standard page. And Jason, from a general rule of thumb, when I think CNC machining, I look at any dimensional, like distance-wise or diameter, I'm thinking about 5/1000ths of an inch. Is that right?
That's correct.
Yeah.
Yeah, our general tolerances for CNC parts, for metal CNC parts, are 5/1000ths. When we go to plastic, it goes to 10/1000ths. You can always adjust that on the website and make it tighter if you need to hold 5 or even closer than that.
All right, so yeah, so general tolerance is 5/1000ths of an inch. For reference, a sheet of paper, if I take a caliper to that, is 4.5/1000ths. So you're still taking a very tight tolerance from a general standpoint, because CNC machining is a precision process from the get-go. When I talk about items like parallelism, perpendicularity, and other features that we're going to talk about later where GD&Ts may come in, you do want to understand that the longer that feature distance is, there is a creep in tolerance. So if I'm making, for example, a piece that is 3 inches by 2 inches by 60 inches, I need to understand that some of these things like a perpendicularity feature, parallelism, straightness, there's a lot of things that can happen with metals when it comes to internal stresses, when it comes to the actual machine itself and how it's machining, how the part is fixtured. So that's why those tolerances get looser over longer distances. Other thing to note here that I just want to mention is that sharp edges, unless it's called out as a critical edge, we're going to break those edges, usually with edge break in the machine, or we'll hand deburr those parts. So when we talk about these distance tolerances, there's usually 3 categories when you're reading this. Most common is going to be that bilateral. So even when I'm just talking about our general tolerances, I say plus or minus 5/1000ths. And this is showing that this green is my edge here, and the range where I'm going to accept this part is within that 5/1000ths on each direction. So it's actually a 10/1000ths long window here. Unilateral is usually where there's a hard stop. The way that I think about unilateral is, say I need something to fit inside something else. So for example, I have a drawer and I have a cabinet. A drawer, I may have a unilateral tolerance for that drawer, saying this drawer literally can't be any wider because it won't fit into this cabinet cavity. And so I may actually use unilateral tolerances to say, like, this, it is designed to this, but it cannot go further than this, or it cannot go within this. So for example, the cabinet may have unilateral on the other side. Limit tolerances are similar to bilateral, where they are showing you the range by numbers. The difference for me that I see a lot of times, bilateral is by far the most popular, but limit is sometimes inspector focused. So it gives you, whether you're an inspector or the machinist, a very quick reference without doing mental math on a spot check. So say I'm doing an in-process inspection, it may be worthwhile to put a limit tolerance on something really critical. Where else do you see limit tolerances, Jason?
Usually you see limit tolerances on critical features. Things that you want to have 100% inspection on, stuff that you want your machine operators checking as they're coming off the machine. They don't have any calculators that they need to use. They just, hey, it's within this number to this number. It's a good part. Makes it almost foolproof.
Yeah, it's interesting because I actually was looking this up because I was making these graphics here, and I was thinking to myself, like, when do I use limit tolerances? Because I know I use them, but why do I use them? And actually had to think, a few steps ahead, and it's like, all right, it's for that quick reference inspection, saying this is good, and allowing you to move on with just the drawing. So let's talk about specific tolerances. So we have our general tolerances. We have ways to talk about distances here. When I talk, and I'm going to talk about a little bit about fit for a second, but really we're going to go into GD&T much deeper on this. So clearance and interference fits, very simple math here, but it's something to talk about when we talk about how to tolerance parts here. Clearance, if you see my graphics here, is when any condition of A, which means in that plus or minus range, so say that A is at its maximum condition, is still less than the minimum condition of B. That's what I call a clearance fit, which means that no matter what condition, as long as they are in tolerance, the feature A will be able to fit within the feature B. Interference fit is going to be the opposite, that would, no matter what condition this material A is at, there will be some level of either a friction or face-to-face or something that you need to actually use a tool or press to install style fit to it. So when we talk about clearance and interference, we're talking about the tolerance range conditions, not just what's designed to CAD, but how it's actually marked up in a drawing for whether it's clearance or interference.
And you'd be surprised, Greg, how many people design things to finish out size for size.
Yep.
So a 1/2 inch diameter hole with a 1/2 inch piece fitting into the inside is not going to work.
Yeah, and you can even, I mean, I've even seen situations, so say you have like metal and like metal, like aluminum, you could actually accidentally cold weld parts together with that, which is why you use different metals sometimes when you're looking at assemblies, especially pins to parts. So we have distances, we have diameters, all that stuff is fairly simple with those bilateral, unilateral limit tolerances. But when we're talking about feature sets, we need to talk about a universal language that is translated between designers, machinists, and quality. And this is geometric dimensioning and tolerance, so GD&T. It's a symbol-based system for communicating these features. The most important thing is that this system uses datums as references on your part in your part design. So in this example here, I have a design, I'm using something called third angle projection. So imagine this is a drawing where it's a square feature. It has a counterbore to it. So if I tilt it over, so this is actually the left-hand side of the feature, if you will, you can see the counterbore outline to kind of give you some orientation of the third angle projection. But my datums are the bottom. So if this part was like this sitting on a table, datum A is the bottom. The face facing me is datum B, and the left-hand side face is datum C. This is very important because every dimension that I reference on this part should dimension from one of these datums. And Jason, from your side, like, what are you machining towards when you see a datums on parts?
Yeah, I mean, as a machinist, we're looking at your datums as those are the main touch points for your part. So we are going to use your datums to set the machining centers up and use A, B, and C as our zeros. That way, when we cut the parts, if there's any small variation, we're always going to be in tolerance, and it's always going to be measured from those edges. As a quality inspector, when I set up my coordinate measure machine, I'm going to set it up off of A, B, and C. That CMM is going to reference those locations for all the dimensions on your print. And so it makes it consistent throughout the manufacturing process that everybody's making it to a certain edge, everybody's checking it to a certain edge, and then when you go to assemble your parts, those datums should be important to your assembly, so everything should assemble right up and it shouldn't be a big deal. If you don't give us a datum, we could be measuring off the wrong edge, we could be manufacturing off the wrong edge, and you could get the wrong tolerance stack.
Yeah, and this is, I mean, even when you plane the blank, so even when you're running a face on your blank material, you're facing these datums because that's going to be the most critical reference area as you fixture your part. So calling these out is extremely important, as well as how you put your dimensions. So for example, I wouldn't put a dimension from here to here on a hole if that's a non-datum feature. I would look at from this whole location from B to C, or sorry, yeah, B to hole or C to hole, or if in this case we're talking about true position.
And the other thing that you want to consider when you're setting up your datum scheme, try not to put a datum as a point out in space.
Yeah.
Because as a manufacturer, you can't really adjust for that. You have to do a bunch of math, and then all of a sudden, you're not really going to get exactly what you're looking for. You'd be surprised how many engineers datum off of a part that's in an assembly that nobody's making.
Yeah. And that's a point. It's like a lot of times I'm using a probe and I'm touching off. I'm finding that using a Xometry probe, so you need some physical space. And I'm getting a little ahead of myself, but say you do have like an internal curvature that has a center that's out in space. Sometimes it's actually better to use a tolerance, like a profile, like a line tolerance, to cover that within a GD&T than to use that as a central datum for that feature. Just very quickly here, if I was covering all these, we'd have a week-long lecture series. So we are covering the highlights, the most popular ones that we see all the time, or that are used, or also sometimes the most confusing ones here. But just understand GD&T, it's a series of symbols. This is your cheat sheet for the symbols here. So when you see these on a drawing, it's talking about one of these, like true position, profile, runout, for example. So let's talk about true position, because it's something that I see all the time, and it's something so important, because again, when I'm designing parts, it turns out they're not floating in CAD space their entire life. They're going to be made somehow, and usually they're going to be mating to something else. True position, the best example I think of with true position is when I'm have an array of holes on one part, and I have a cap, enclosure, or off-the-shelf item that those holes need to mate up to. I'm using true position to essentially group those features together to say these holes as a set, they are within this GD&T tolerance and true position, will confidently mate to the other piece, even if other piece is made in a completely different manufacturing place, like it's an off-the-shelf item or it's made with a different manufacturer. By using true position, it allows you to give that confidence in your design and through your drawing and through our inspection that the parts you receive will fit together. So it's typically used for locations. It is talking about this wiggle area for these features, and typically a feature set. Jason, we talked about that when we're machining these, we want to make sure that the parts clamped in one location, and we're machining them all in one step to get the highest level of confidence that these features will be produced correctly in true tolerance. But this is what you would typically see on a drawing.
Also, you want to consider when you're putting your true position tolerance on, that it is roughly the X and Y locations are roughly 1/3 of what's called out in that box. So, a 14 thou is a little bit more than two thou positioning on X and Y that they can be out. So just take into consideration, you'd be surprised how many people put on a 1 thou true pole position, and that's not really reasonable. Those CNC machining centers have more error than that. So just consider your tolerancing when you're doing it. Obviously, tighter tolerances make the price go way up because it requires more setup, it requires more stringent checking of the part in between actually running tools, and just adds time overall. So.
And it adds risk to that too. Yep. So anytime you're tightening a tolerance, especially if you're making an over tight tolerance for the actual purpose of the part, you're incorporating risk, which could add lead time, increase scrap rate, you name it, and you may not always need that work. So just to talk about interpretation of this, this is a very typical thing I could see here for a countersink hole. So I have 6 holes here. I know the diameter is 102 thou. I know those asymmetric dimensions here, so +3, -2. I have the countersink information, that little V there, about how wide that countersink is, its tolerance as well. And then I have this true position call out. So relative to the faces that are called out from these datums here, I have this diameter. This is the wiggle room essentially, right?
Basically,
Yeah.
There's a calculation done,
Mhm.
and basically your part can fit into an imaginary area outside of the normal CAD.
Yeah, so I put these circles in to kind of show this reference, like this is my true position area, saying like as long as these sets, even variation between sets, as long as these sets kind of hang out here, I have relatively high confidence, or it should be almost absolute confidence, that these parts will be able to mate with their mating assembly. The other common features that I see very frequently in drawings and parts that we make here, flatness, parallelism, and perpendicularity. These ones are fairly self-explanatory, but I do want to talk about how they are measured a little bit. So flatness, it's a non-datum callout. It's just calling out a flat face, and it's talking about the acceptable variation of the plane. So I have a flatness callout on this on this plane here, and what I'm going to actually be doing is measuring from this plane the deviation across it. And if I find that the deviation goes beyond 2 thousandths, I am out of tolerance.
And that is total indicator.
Yes. It's not plus or minus, it's 2 thousandths total on this feature. So I'm looking at that entire plane. I'm creating the kind of virtual nominal plane and looking at my max and mins. And if I find that any movement is beyond 2 thousandths, I am out of tolerance there. Parallelism, I actually playing this out of 2 thou to make sure that's nice and flat, because I want this other feature here to be parallel by 30 thousandths, my acceptable criteria, to datum A. So referring to this datum A, which is also the part that has the flatness callout, I want to make sure that this feature here is parallel within this tolerance, and that's what parallelism is looking at relative to this one, how parallel are they? And in this case, I'd actually take datum A, I'd put that piece down on a granite block, and I can run an indicator. I could do this via CMM as well, but I can run an indicator and see the movement of that indicator. And
or you could use mics.
Yeah, you can use mics on it for sure. Yeah. Perpendicularity is looking from a datum to what level is my 90-degree feature coming out of that part. So in this case, again, I made this piece here. I put a little external lip. You guys should be congratulating me for how well I'm doing on my PowerPoint slide. CAD graphics, by the way. But this is harder than you thought. It took longer than I thought it would take to make this graphic here. But yeah, it's taking a look at this datum B, which is this flat face here, and what my acceptable range is for how perpendicular this feature. Again, 3 thousandths relative to datum B. All GD&T other than flatness basically has a datum callout. Again, so you always are measuring based off this datum how these features line up. The other common ones that I want to go over is concentricity and profile tolerances. So concentricity is the acceptable deviation from an axis. So a lot of times you'll see an axis. Sometimes you see the datum actually called out on the axis itself. Sometimes you see it on a cylindrical face. With concentricity, it sometimes makes more sense to call out the face itself. But imagine I took this axis over the entire part and virtually segmented it right here. When I ask for a feature like this round feature to be within 30 thousandths concentric to this datum, what I'm actually doing is segmenting out this virtual axis to datum A and seeing the deviation of this axis. So how much wobble does it have as a feature compared to this datum, and this is my acceptable criteria. This becomes very important for machining, right? So like you would completely change your setup, Jason, and like tell me a little bit about that. Like what?
Yeah, so you know, round parts are usually made all the lathe, right?
Mm-hmm.
So depending on what kind of concentricity callouts you have on your part, if they're a little looser, obviously you're going to try to do as much work on the first operation as possible, but that's not always feasible. Sometimes you have to flip the part over. When you have a 30 thou callout, you're just going to put the part in a collet or in some jaws, and you're going to run the next piece, and you're good to go. When you have a thou concentricity callout, all of a sudden you're going to put an indicator on it. You're going to tap in each part to make sure that it's got 0 run out in the machine before you make, the next side. And it amplifies your setup time, amplifies your load time a little bit. And obviously, depending on the tolerance, it's going to facilitate more checks on the shop floor to make sure parts are good.
Yeah. And absolutely, in this piece here, so again, my demo piece using my stock art, I put a little half moon shape at the top here. So this is a very tight concentric call out. I actually may opt to do this in 2 separate machine setups where I may turn out the main features of this, leaving this as a round, and then change my operation to post machine mill this using a vertical mill. If it's looser, if it's a looser tolerance, I may be able to make that entire feature in an operation on a 3-axis mill. So it really depends on what you're calling out there, and as Jason noted, changing some tolerances can actually change not just how you approach the machine, but what machine you're approaching to make that feature. Profile and surface callouts are a little bit different from a lot of these because they're looking at either if you take a virtual plane across a part and you're measuring out those different features, it's a deviation from that CAD nominal profile to what's actually showing up, so that maximum allowable deviation. For the line profile, this is an okay call out for the example here, but in this case, you're looking at this round circle, and I'd be tapping along to see the level of deviation around this relative to essentially the center of the part, and the flatness B here, which is going to be the flat base of this, and looking at this deviation. A lot of times you see it more for curvatures on surfaces. So I'm using this or even gear features. So I'm using this for example, but a lot of times you see it more on slight curvatures, spline features where profile line comes out. Surface profile is going to be, say I have a custom keyway or something that's in a 3-dimensional space or 3-dimensional surface. This requires CMM to inspect, because I'm actually creating a virtual map of the touch points of this part and saying across this virtual map in this 3-dimensional space, what deviation am I seeing from the CAD? And in this case, you'll see the kind of half moon feature there. That is a surface profile. Just understand that if you click surface profile, you're asking for a CMM. So that one feature added to your part could add a $300 inspection operation. Or more.
Depending on how complex the part is. Yeah. The other thing is, I've seen a couple engineers that they use surface profile, as their only tolerance on the part. Don't do that. It makes inspection a nightmare. Then we have to CMM every hole. And when I say CMM, I'm not just doing 4 touch points to make sure the hole's where it's at. I actually have to do a scan of all the holes, all the features on the parts that then have to be scanned. And then, we get a report out from the CMM that says it's good or it's not good for the whole part.
Yeah.
And then there's no real dimensional call out. So if something's out of that profile tolerance, we have to go back and then figure out what's out so that we can figure out what's going to, is the whole position off in X a thou out of tolerance? Is that what's throwing that profile out? It creates a nightmare.
Yeah, and this is honestly, this is what we talk about when we talk about over tolerancing, and also calling out what's critical for the purpose of the part, because general tolerances of the process itself cover a lot there, and it is very tempting to say, oh, this surface profile, my entire part is 30,000. So if you're within it, you're all good. But as Jason said, technically for me to inspect that, I need to scan the entire surface, and that is equipment usage. There's no way, shape, or form about other than that. It is a separate equipment, and setting up CMM and setting up some of these scanning equipments is just as much setup as creating a CNC machine program. Hey, look at that title block. So yeah, your title block should reflect the process that you're selecting. So title blocks are used to cover general tolerances. So you can see here, very common title blocks. So 2 decimal places are giving me 10,000 squiggles. So that may be something that is it's a feature, but it's a non-critical mating location. 3 places is a 5 thousandths general tolerance acceptance, and an angular tolerance is going to be anything at an angle off plane. If I'm measuring the angle there, I have a plus or minus half degree deviation to that. I really like it personally when I have a title block like this for CNC machining. I've seen some times where the title block gets tricky, and now our engineers, we take a closer look at this where the 3 place all of a sudden becomes a 2 thou. Sometimes it's better to use general tolerances and then call out those features on the drawing to make sure we bring eyes to it, because it's something that can be easily missed, especially when you see title blocks on every single part you're doing. And I would say 99.5% of them have this standardized tolerance range.
The other thing I would say is don't use hybrid prints. I've seen several customers that they call out, plus or minus 5 in their tolerance block into inches, and then the rest of the print's done in metric. Or they have some metric tolerances here, and they have some English tolerances here, and then it gets very confusing for QC. It gets very confusing for the machinists. And it's just, keep it simple.
Yeah, and this is true. Like when you make a drawing, it's not just copy and paste that template and putting out your measurements. Your drawing is a love letter to your machinist. Like it's the first date, and you want to build that relationship and give a good impression to that, because we want to make great parts for you. And our quality assurance team will make sure the parts you make are to spec. If we have, if drawings inherently have confusion, like for example, a deviation on title block that wouldn't typically be there, or confusing units, a shorthand, a red line that may not be easily interpreted, all that stuff can really matter when it comes to manufacturing, especially when you start moving into production manufacturing or manufacturing where you're building multiple parts that are to be assembled. So let's talk about over-tolerancing a little bit and some alternatives that we have. So I always like to bring this up, especially because, again, my background a lot of times is in that 3D printing space, and there's more tolerance creep than machining for sure in that area. I like the usage of slots where I may make an anchor location, which may be my feature location, or sometimes a dowel pin location, to say, hey, these features mate really well here, and this could be a tight tolerance location. But for the other features, I can use general tolerances if I use slots instead of holes. It doesn't need to be as generous as this feature here, but you could even making a hole where you have a pass-through slightly elongated can go a very, very long way in how many tight tolerances and how difficult the machining and how costly that part can be. So just highly recommend when you have the chance to use those, using slots is really, really useful to prevent over-tolerancing and increasing the price of your part. The other thing is be ample on your clearance fits. I don't want to reject your part for a counterbore hole or for the counterbore feature, but it is something that can be overly generous on the design, and we measure it. So if you have tolerances there, we're going to measure that. But just understand that you can make this looser, because the whole purpose of that feature is to allow for clearance of usually off-the-shelf fastener. So in this case here, imagine I'm making this light blue block to this dark blue block here. You can actually see that the gap difference exists on these, but you're still getting a mate of these parts. So I'm creating ample clearance for these features so that deviation on this part doesn't completely fail the function or make the part as a rejectable feature. On this note here as well, like I have a lip mate, so imagine this is a cross section of a mating feature where I have lips to index those features together. If you build flush to flush, understand that, again, deviation is reality. And if I have a deviation here, that means I'm going to have a lip gap here. So it may actually not work for my cosmetic needs. Same thing on this side, or same thing over here. I may be pushing this direction or that direction. So choose one. If you want these things to hit flush here, create a gap here and here. If you want this to have a flush outer finish, like this piece here, you make these flush to flush, creating ample clearance here as well as some clearance on these areas. and you're going to have a much more successful, much more repeatable product line. So I mentioned some indexing features there. Dowel pins, again, very useful. They're cheap. They're already precision machined. They're usually 4 decimal places machined out. We can use a reamer to make those holes and sometimes do a press fit, for example, on those. And it's just one click away on Xometry's website. And a lot cheap. And it's cheap. As I said, again, it's so much cheaper than making a custom, vertical protrusion feature at a super tight tolerance. It's drilling a hole with a reamer and pressing a dowel pin is standard practice. It's very successful, and sometimes to get those critical tight tolerance mates, you could make those dowel pins as your index features, and then use fasteners with a looser tolerance to hold everything together. So just really recommend think outside of the box. Sometimes think about integration and assembly. Using these off-the-shelf features, they're off-the-shelf for a reason, because they are common and they are useful. The other thing to note is when you're creating clearances, when you're creating tolerances, those tolerance ranges, we're building parts from reality again. These parts are usually made with other things. I have my GD&Ts to make sure that things are aligned, but I also want to be aware of maximum conditions, minimum conditions, and variations in between my conditions. So stack up, it makes a lot of sense, especially the more stuff that you have mating together. You want to take a look almost from a plane this direction, and see what my stack up is to make sure that if, say, for example, this feature at their maximum tolerance range is this direction, and I put a bolt through, all of a sudden I can't get my nut fully secure on the bolt. There's lots of examples of this where stack up can cause an issue, especially when you're going between processes. So I have my electromechanical assembly. I have PC boards that have their own specific tolerances to them. I'm sandwiching that right in the middle, screwing these 2 assemblies together, and they're sandwiching the PC board. And all of a sudden I find out I have a gap that I can't actually do a lip seal, O-ring seal around. So you actually may want to look at, maybe I don't put that board in the middle, maybe I make a boss feature that goes around that board, so I just have these features. There's other ways to work around this, but just be very mindful. As the more integrated, the more stacked parts you have in your assembly, stack up can become a real issue in a production line. I'm not sure what else to say about that. Oh, actually, the other thing is parts are not always made in the same location. So a lot of times the testing of those final pieces and how they integrate together, especially from various processes like a mold part, machine part, sheet metal part, if they're all getting made together, the first time they may be together in one place could be at your doorstep. So just understand, again, that's why GD&T exists.
It's easy though on the website to note that certain parts need to be made with other parts, and then we know to do a mate check. When we source parts to our partners, we'll source parts that need to fit together with each other, and it'll just generally keep it simple. The more knowledge that we have about what's going on with your parts, how they're being used, what's going to fit where, the easier it makes for us to manufacture, and sometimes we even catch problems for you.
Yeah.
Where we can see, oh, if I made this part and I make this part, and one's at the max and one's at the min, they're not going to fit together.
Yeah, and we're curious too. So those notes in the notes section of your drawing, it's very helpful to communicate that. As Jason said,
real people see these.
These are we're not robots here. We actually, and I'm not sure if how much you guys have interacted with machinists, but they're also artists. They're passionate and they will fixate on a problem until it's fixed. So as long as we know what to look out for, we're going to keep an eye open for it.
We're all a little OCD.
a tad OCD. So what can you do again to make this love letter to your machinist better? CAD best practices. We're in a new age. The PDF is not king anymore. CAD is king. PDF helps guide my eyes towards what tap tools, what those threads are, those tight tolerances, those GD&T features. But my CAD is actually what I'm using for my digital upload, quoting that product. The CAD is what's transferred to the qualified machinist to make your part. The CAD is then used in their CAM software, so computer-aided manufacturing, interpreting what tools are required, how to actually process that part, the setups, the fixtures, it's all done virtually in this virtual machine to prevent any errors, and then it gets made in reality. If there is a deviation in your CAD that from what you need, we're going to cut it that way.
We're making it to your CAD. If your drawing is the wrong rev, and you give me a CAD model and you give me the wrong rev drawing, I'm making it to the CAD model.
Yeah.
We may put your part on hold and reach out if we discover it in time, but a lot of times, those parts are made and they're put into inspection, and then the inspector is like, hey, this CAD and print don't match. This whole position's off by whatever. Nobody has time to measure all the features on a part before they machine it.
Yeah. So the things that we catch that are usually the mistakes are when a hole for a tap feature is too large. We can always make holes larger, but we can't make them smaller. So if you have the maximum tap condition in your feature set, if we drill that out and we don't catch that, then a tap's just running loosely inside. It's not going to be cutting any metal. So always use I use hole wizards religiously. So those take the risk out of it. But making the feature to the minimum hole tap condition.
Always to the minor diameter.
Minor diameter there.
So if you make it to the minor diameter and you forget to give us tapped holes on your print, it's a good chance the machinist is going to recognize that hole diameter and question whether or not that should have been tapped. That's the other.
Yeah, you see like what it was like 0.214 all the time, and you kind of know that there's a tap feature there. The other thing that I see a lot is when we talk about those unilateral tolerances. If you have a part that cannot go less than 1 inch, and you design it at that 1 inch feature. So say it's -0 +10. I actually recommend making your entire part to that middle, like right in the middle of it, as if it's a bilateral tolerance on your 3D CAD. That allows us, we're gonna make sure that it's in spec to your drawing needs. But if you're right at edge, there's a chance that when we cut it on our first pass, if we're following that CAD, we may have accidentally made that part out of tolerance to your drawing. So there's always intention behind your CAD design. And it's that love letter. It's how to mitigate the risk down your entire process. Drawing best practices, reduce clutter. If it's a general tolerance, your title block usually covers it, or the process itself inherently covers it. We want you to call out what you want us to measure. And I'm about to go into inspection processes. So again, if I'm doing a bubble drawing of your part, I don't want to bubble every single geometric dimension on this. I want to bubble the things that are critical to you, because the rest of it usually is covered with the manufacturing standards that we have here.
Yeah, the other thing is, if you're designing a print and you're finding that your dimensional features are overlapping each other, it's very hard for a QC to figure out what line goes where. And so it makes it more difficult. So that's use that tolerance block as much as possible, and use multiple pages on your drawings if you have to. Yeah. Don't try to cram everything into one page. It doesn't hurt anything in a PDF to just pull up page 2. It works well.
Absolutely. So let's talk about bringing it back to Zometry, how to specify these. Again, you're a couple clicks away. And I also want to get to some of these questions that have been coming in as well. Once you upload your part, you specify your materials, features, and finishes. Right now I have this drop down for CNC machining, and specifying tolerances to get the price appropriate is as simple as specifying what the tightest tolerance is, so the closest one you have here. So say it's like a 2,000 tolerance, it's the tightest of the 4 tolerances that are below general tolerances there. Select that 2, and then select the locations of total that are below general tolerances. So usually below that plus or minus 0.005 of an inch there. If you have GD&T measurements, usually a good practice, although it's as Jason said, sometimes the more holes you have, the tighter and tighter and tighter the tolerance is. But a lot of times it's taking that tolerance, subtracting 1,000 from it, and that's going to be what you're going to select as tightest. Either way, our AI-driven manufacturing algorithm to determine pricing just really needs what's the tightest tolerance on this part and how many tight tolerances are there, and it spits out the price that's accurate for you. So it's very simple to upload, select, count, and then attach your drawing for reference. So Inspection methods differ between the parts and their features. If I have things like surface profile, true position, a lot of times, concentricity callouts, I may be using a more mechanized tool to inspect those, depending on the complexity of those parts. So just understand that when you're looking at your part and your design, that sometimes a certain feature, especially large spherical contours, or off-angle datums, datum call for, like, say it's a manifold with multiple port features, that's probably CMM. So just understand that you don't select for like the cheapest inspection if you know it requires CMM, because it'll probably require CMM if that's your feature set here. So this is a little busy. We're gonna have some copies of this at the end, but to talk about what we select on our inspection reports. Typically, when you upload your file, you don't have drawings or anything, and you just press go. We have our standard inspection, which is we're going to interpret, if we don't have a drawing, what we think the most critical dimensions are of the part, measure those out, create a report internally for us, but we're not shipping an inspection report with that. If you do require a formal QC inspection report, click the radio for formal inspection. We'll do 100% dimensional inspection following standard QA sampling procedures, and we require a print. All these other processes build off of that. So if I require a CMM inspection with a delivered report, clicking this is going to add the CMM inspection plus probably some extra time to build this out. We require a print. You get a balloon drawing back with that digital readout, that digital printout of our CMM inspection report. We also, Zometry is an AS9102 company. If you're working in aerospace or defense, a lot of times you need to hit that compliance. Clicking this first article inspection report requirement allows us to get the proper documentation. We're going to actually build your full sets. We're going to run through that final inspection with a fair report for you. Understand that if you're looking for us to make one part, fully qualify it through with first article inspection report before we start on any subsequent parts in a production order, we're going to want to treat those as two separate orders because they'll have two completely separate timelines to them. It's something where you may choose custom inspection for that to make sure that we're aware of what your intentions are, and we'll create that quote out specifically for you, usually in a couple quotes, so that you can order both at the same time, or we're able to start one, run through the process, wait for your approval, and then reproject the due date for the second one to make sure it goes through the process appropriately. Source inspection is, clicking this is going to do a audited inspection of the process and records at supplier premise and to verify the compliance. So this is, we have our internal QA, we can also do source inspection to make sure that everything that they're documenting is audited.
Normally, source inspection, you want to watch me inspect your part.
Mm-hmm.
This is going to add a lot of lead time because I got to fit it into my schedule. Mm-hmm. I don't recommend it unless you absolutely have to have it.
Yeah,
but there are certain companies that have moved to source inspection. Some of the large aerospace people,
yep,
they come and see me every week, and we run through our CMM program with the parts.
Yeah, and those who absolutely know they need to have it, like you'll know if you're in that company that you need source inspection. So it's a very specific requirement, but we definitely work with the top aerospace companies, and we do see it, so we have that required. We have it as a one-click option on Zometry. So this is a lot, guys. We just talked about something that's usually, again, a lecture series on this, and there's going to be so many questions to go through. I want to spend the next 5-10 minutes going through questions. Just very, very quickly, I know Serena has a couple of things, but we have FAQ, live engineering support at Xometry.com, 8 a.m. to 9 p.m. Eastern. We're available for you. You can call us, you can live chat with us, shoot us an email. But we're happy to talk through whether it's a question just about the site, general knowledge, sending a PO, or trying to ask for a technical expert's opinion. We're here to take a look.
All right. Before we get to the Q&A here, we have a special discount code for all of our webinar attendees. Thanks for sticking around. If you enter in Zometry CNC in checkout, you'll get $50 off your next Zometry order of $100 or more. This discount code is available through the end of August, so you have time to get your questions to us and figure it all out. We also have a special offer. When you quote today between now and midnight, we will give you a free Apollo 11 t-shirt in honor of the 50th anniversary of the moon landing. So this is limited edition. Also, for every instant quote or order, you will get a free entry into the sweepstakes for our ice press, and you can see it working its magic there. So get those orders, get those quotes in today for that t-shirt, and then potentially for the ice press as well.
The ice press is actually pretty cool. I had no idea what this was, and then I watched it, and like this is like near real time. It took like 12 seconds to make essentially the landing module for once the reentry module, I should say, shape for ice. So I mean, I thought that was a very cool thing. So let's get to some questions. Yeah.
All right. So Greg and Jason, we have over 10 questions here. So
All right.
First one here. Most people prefer to use true position and run out to control the axial feature instead of concentricity. Can you explain the reason why?
Maybe it's easier to check. I don't know.
It could be easier to track because you can
put it in a V block and you can check it with an indicator easily.
I think that makes sense. Yeah, because you could do it all on granite.
Okay. Next question. When I specify a datum surface, does Zometry automatically machine that surface so it can be reliably used to measure from? And if the datum is unmachinable with variance, how do you use it?
So, like we said before, if you have a datum surface, that is what we are using as our setup surfaces. So we are machining that surface on the blank, and then we are using that in every operation afterwards to locate the part. If you have something that is off the part, then it becomes difficult and we have to do math to calculate back to an edge or back to a hole so that we can locate. So that's why we're saying always try to make your datum a spot on the part, or give us like a tooling ball location that we can use or something like that.
Yeah, the datum feature is usually a flat or a round or a line type feature to it. So that's really important to note, because if you do have a nonlinear feature, it becomes a math problem, and sometimes it becomes this weird rubber banding effect where it's make it, determine it, see if it's in spec, which is kind of the opposite approach. We actually want to true everything up and then machine to the true to prevent risk on the first op for sure.
Okay, great. Thanks for those questions, Han and Steve. A question from Justin. Does Zometry offer cost comparisons across different manufacturing methods, such as 3D printing versus machine versus casted?
Yeah, it's a click away. So if you go into our modified part model, so as soon as you upload those files, your part's already priced out in all these different options. So you can actually just click the process, click the material, you'll see the price instantly update as well as the lead time for those parts. So it's very easy to go and compare between different processes.
Different materials.
And different materials, brass, aluminum, or 6061 to 7075 even. Just understand that each one of those has its own embedded and inherent costs, lead times, and other associations. We price based off market-based pricing, which is essentially based off our entire manufacturing partner network of who can make those parts the best and most reliably, what is cost competitive for them and for you all. And we're determining that using essentially AI machine learning. So we want to build a fair market price system, and it's based off our manufacturing partners, which are highly varied in what they're skilled at, and it actually helps us drive costs down while driving reliability and quality up.
Similar question here on resources. Is there a resource on your website that you could provide that outlines how to calculate the required true position based on hole and pin clearances?
Stay tuned. Actually, we're building our knowledge base, and CNC is one of the first things that we're shooting out for. I know we have some links for some calculators, but I actually I'm going to make note of that because that's something that we're working on actively right now.
So there are also apps for your phone that do that.
Yeah, it's amazing. Our QA team is they're like I've seen someone manually do true positions before with pins, gauges, measurements, hand math, and now there's apps being like, how many holes? What's the distance from here? Tap 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 in. It's actually more advanced in the industry, and now now you have peripheral devices like apps for that.
Great. So can you do a flatness callout on the datum plane?
Yes.
Yeah, absolutely.
All right.
That's probably the preferred spot.
Yeah. Flatness is non-datum just because it's saying this plane. It doesn't refer to anything else. It's just saying this face. What's the deviation of it? But you can definitely add flatness to a datum plane, and honestly, it's pretty common because usually you're measuring off of that anyway, so you want it to be to a certain level of flatness.
Quick and easy. I like it. All right. Is it assumed that the profile callout is based on the solid model?
Yes.
Yes. CAD is king.
And regarding flatness, how would you check flatness on A if the parallel face isn't machined yet?
You can't easily check it unless you use a coordinate measuring machine.
Okay. Question from Patrick here. How would you show a dimension like max R 0.005 in a 3D model?
So you're talking about the maximum radius of maybe a protruded feature or a hole, I'm guessing. So that can, like, a lot of times that could just be a distance unilateral dimension. So if you do require, like, if you have a hard stop max, it may be as simple as that plus or minus to talk about that dimension. If I didn't interpret that right, shoot me an email and I'll make sure to interpret that correctly. But yeah, sometimes that's going to be a distance measurement, which could either be, if it's a positive feature, I'm going to bring calipers to it. Or Mike, if it's a negative feature, I can use pin gauges.
Okay, question from Mark here. How do you accommodate and adjust operations and costs to get the most value from feature modifiers like MMC?
Maximum material condition.
Yeah.
We were just talking about something. Yeah.
We don't adjust costs for maximum material condition at this point.
Yeah. This actually comes down to also what does it, like, maximum material condition and these other things, it still brings you back to a GD&T tolerance that needs to be measured. So a lot of times, just like setups on quantity one parts in CNC machining, a lot of that cost is already driven in the fact that you are measuring to GD&T in the first place. So right now, our algorithm is not really differentiating that because the operation in which we need to inspect it already exists. Essentially, if you're working with a true or type
Also, we're not automatically reading your PDF.
This is true.
We're relying on you to tell us what your tolerances are, and we go based upon that tightest tolerance and the amount of those tolerances. The GD&T is all the inspection process. So.
Okay, question. Let's
do 2 more questions.
2 more questions. All right. What software do you use to generate AS9102?
Okay, so we don't use a specific software. We use SolidWorks inspection tool to bubble out the drawings and make an Excel template. And then, we use, depending upon what the part is, we either fill in the Excel template using manual tools, or we dump a CMM report into that.
Yeah. Something to note too is that the backbone of Zometry is its digital traceability. So inherently, from you using Zometry to specify your quotes, your preferences, we're tracing essentially by the minute the process and procedure of this part's life, from digital upload through to acceptance of the partners, which partners take this, the partners' digital traceability of where they've been on this part, the process steps, their uploads of their own inspection reports, in-process needs, packing reports, when this part's been packed, like all this stuff happens digitally. So just like I always talk about, like, I like to focus on just making good parts because our system inherently has this quality traceability to it. The same thing with quality inspection. They're interested in seeing if this part passes through. Like, they're looking for the deviations, but the actual reporting process and the traceability is inherent within Zometry's platform.
Okay, and let's do one final question before we let you all get back to work. Again, if you didn't get your question answered, please feel free to follow up with Greg and Jason.
And we're going to look through all these questions as well and follow up with you.
And reach out. Yep. Okay, so last one here, a bigger question. Do you ever deal with optical tolerances?
Like, I'm going to interpret that as grinding and high polish grinding. I'm going to say that is specialized manufacturing. So we have done sometimes the process and tolerance is very, very tight, and that's where you would select custom, for example, on these, and actually that's more like a custom finish, because once you get down to these tolerances, it's not an end mill making these. You're usually moving to a separate manufacturing process altogether, wire EDM, grinding, RAM EDM, and so this is a combination of processes performed to this blank essentially to make that machine part. That's when you talk about optical machining, and these things are honestly as true to perfection as you can get. Yeah, all of a sudden you're in a very, very specialized world. You're way outside of general manufacturing.
Yeah, it's something that if we were to quote it, we would go to an outside inspection house to have them do the special inspections.
Yeah. Just one last note, and then we're going to close this up. When it talks about inspection equipment, we're usually one measuring equipment that can measure 1/10 of what that dimension is. So, for example, if I have a dimension that has 3 decimal places, I want to make sure that my inspection equipment can measure in confidence up to 4 decimal places. And so that's why all of a sudden, like a caliper may become a mic, and then that mic may become a CMM. There's depending on how many decimal places and what you're really looking for in that part.
All right. Thank you so much, Greg and Jason, for being here to talk about machine tolerances. Please feel free to follow up with any of us after this webinar. We hope it was useful. Quote before midnight for your t-shirt, and be entered into our sweepstakes for one of 5 custom CNC machined ice presses. So thanks again, and we'll see you in the next webinar.
Thank you, guys.